Chapter 5 practice test. So we have a 1 liter solution. So all our moles will be in 1 liter, which means the moles are equal to the molarity because we're going to divide by 1. So we put in a weak acid and a strong base. So all the OH minuses are going to come off and rip into the acid. So if I put in 5 of these, I'll rip off 5 H pluses, right? So if I put in 0.016 moles of OH minus, because all the Ks are going to come off, I'll rip off 0.016 moles off the weak acid. So here are my beginning molarities, because remember it's in 1 liter, so the moles is the molarity. Of course, I have none of these products, and I don't care about the molarity or moles of water. So here's my starting moles. As I said, one of these will rip off one of those all the way until it's done. So 0.016 will rip off 0.016, leaving 0.004. None of this is left, but when I rip an H off of this, I create one of those. So ripping off 0.016 or destroying 0.016 of these creates 0.016 of those. So here's my final molarities. And the little trick is that K plus was at 0.016 and this is at 0.016. So actually these are equal at 0.016 molarity. Again, they're in 1 liter solution. So we can call the moles the molarity. And all we need is a relative comparison, right? So it doesn't even really matter if you're going to divide everything by 1 or 3 or 5. They're all going to change by the same proportion. And this is equal to the K plus, and this is clearly greater than that. In 2, I have a weak acid and a strong base. So this is going to rip into that. And notice the moles are equal. So the moles are going to chew up all of that, aren't they? This is all going to chew up all that, and we're going to have none of either of them left. And when I use up one of these, I create one of those. So what I end up with is only the anion, the base, in the solution. Now, what is that molarity? What are the concentrations of the ions? Obviously, these are 0, but I need the liters to get the true molarity. It's this moles. Remember, this was in moles in 2 liters. So it's 0.8 moles over 2 liters is 0.40 is the molarity. And the Na was also 0.8 moles. Remember, the Na's come off in 2 liters. So we get the same math as this one. So this answer is equal. These were 0. On 3, we have 2 different solutions of the same amount of milliliters, a strong acid and a weak acid. Now, the other striking thing is that they have the same pH, and that means that the H plus molarity released into the water and no longer stuck to the anion is the same. And if the pH is 4, then the H plus molarity in the water released off the anion must be 1E negative 4 in both cases. So which one is better at doing that job at releasing the H plus off the anion into water? And clearly the answer is something on our strong acid list, like HCl. For dumb numbers, let's just pretend. We know that the H plus numbers released are equal, and let's just say 100. How many HCl's do I have to use to get 100 H pluses into water? I only have to have used 100 of them because I know that all the H pluses come off my strong acids. Now, to get H pluses in the water of HNO2, I have to use more of it. If there were 100 released, maybe I had to have used 150 HNO2s. And that means that the KOH I have to put in to neutralize both of these fully, to get them to the equivalence point, is more in this case, because here I have to burn up only this H plus here, this 100 of these. And in this case, I have to burn up this 100 and all the other 50 that were still stuck to the NO2s. So I have to use more OH minus to grab all the extra H pluses. So which solution requires more moles of KOH to reach the equivalence point, and why is that? You have to use more on the weak acid because there's more H plus to grab. There's all the ones it released, and then there are all the ones it didn't release. And the equivalence point is when the OH minuses have reacted with all of them. And there's more H plus to react with in this case than in this one. And this reads as HNO2 is a weak acid and requires more molecules to supply that much H+. We need more KOH to reach equal moles. On number 4, we have a strong base and a weak acid, and this moles is half of that one. All the OHs come off, and of course, they chew up the acid. So this is going to chew on half of the weak acid. So we have the weak acid, and here's the strong base, the OH minus that comes off, and it creates A minus the base and water. Of course, we're going to disregard this as immaterial to the pH and so forth. So this moles is half of that, so it chews up half of it, leaving half and converting half of it into the base anion, the conjugate base of the weak acid. So we have a weak acid in the conjugate base, and that's a buffer. This is now existing at the halfway point, or the half equivalence point, where half of this has been converted into the conjugate. And in the Henderson-Hasselbalch equation, when you have equal amounts of the base and the acid, and remember they're in the same beaker, so their molarities are equal because we would have divided by the same liters, then they cancel out to 1, and we have log of 1, which is 0, which is why we can cross out this whole thing, because the value of this whole thing is 0. Therefore, pH equals pKa, and therefore the pKa is 4.2. Now, a little mental math calisthenics here. If we want the actual Ka, what we need to do is undo the log function that's hidden in the P number, like in pH, or in this case, pKa. And remember, we did the negative log of the Ka value to get pKa. So to run backwards, we have to take 10 to the power of the negative, because remember, this was supposed to be negative. When we take a log of a small number under 1, we get a negative value. But remember, we then take negative of that to get a positive here. So really, there's a negative here. So before we put it back on 10, we have to put the negative back in. So we get 10 to the negative 4.2. Now, if this was 1 to the negative 4, it'd be easy to say that this is the Ka, isn't it? But this is more negative. It's smaller. If we take 10 to a smaller power, we get a smaller answer. So it's not 1e negative 4 or 10e negative 5. These are equal. Hit pause if you need to. These are the same thing. It's going to fall out of this. It's going to be easier, though, if we regard this as 10e negative 5. It's going to fall from here. And it sort of looks like it's 20% moved on to the 5, right? 4.2 is 20% on the way to 5. So it looks like it's 20% on the way down into the negative 5 range here. However, logarithms are more powerful at the beginning of their travel than it sort of seems. So instead of 20%, I guessed it moves 30%. I guessed it would go there. So 7e negative 5 on its way down toward 1e negative 6. And it was just a bit of a guess because it was only 0.2, but the more you move, the more the effect takes place. So I guessed it was either 7 or 6, and I just guessed at 7. And you know what? It's not a bad guess. It was 7 or 6. Actually, 6 was slightly more accurate, wasn't it? Because here's the real number. But this is not too bad for a no calculator guess at the Ka. On 5, we have a strong acid and a strong base, and these are going to react in a one-to-one relationship as the OHs combine with the H's, and they all come off, and they're all going to react as much as possible until one of them runs out. But we actually know that we want to go to the equivalence point because we are going to make a pH 7, which is neutral. So we're going to use them both up exactly on each other, which means that the moles of each are going to be equal to each other. So how many milliliters of this will be needed? Well, I only know the molarity, and I can do it the hard way or the easy way. Let's do it the hard way for a moment. I can find the moles of this because liters times molarity gives me moles. And we said they react in a one-to-one relationship. So this moles of H plus, because remember, get 1 H plus per molecule, is going to be the moles of the NaOH that is needed to react with that, because we want to use them up equally. So we're going to get the same moles of each. I know that this is the molarity, but notice it's flipped so that the moles cancel out and gives me liters, which is 20 milliliters. Now, the easy way would be to say, what's the factor of increase of the strength? Now, just for easy numbers, what if this was twice as strong as that? Wouldn't you need half as much? If this was 4 times as strong as that, wouldn't you need 1/4 as much? Well, it's 2.5 times greater in concentration than that is. So the fast way would be to notice that and say it's a ratio of 0.25 to 0.1, which is 2.5 to 1. And therefore, we can take the milliliters from before and divide by 2.5. And look, we get 20 milliliters. On 6, we're going to titrate a weak acid. Here's our classic acetic acid with a strong base. So the base is in the burette. And burette is a glass tube marked usually from 0, somewhere near the top, to 50 or 100 milliliters at the bottom, so that if you fill it to 0, you don't even have to do subtraction to know where you are. So if you're careful the first time, you save yourself a lot of subtracting and maybe confusion on the way down when you stop at various points and you do various things. So that's why the burette reading goes from 5 to 45, because it's falling into greater numbers as you use it up and you drain this out into the Erlenmeyer flask. So they added some water, probably just to wash the sides of the flask and get all the acid down into the bottom. It doesn't matter, because although the molarity changed, the moles didn't change. All the acid molecules are still in there, and it takes just as much base to react with them. It's the moles that's key here. So this is, by subtraction, the amount of base that we use, 45 milliliters, and it was titrated to the endpoint, which means that the moles of each are equal. So if we can find the moles of one, we can find the moles of the other. And what I have is information about the liters, essentially, and the concentration of the KOH. So let's take liters times molarity gives me moles. I know that they react in a one-to-one relationship, so that's also the number of HAs that was used. And that moles was in originally 10 milliliters. Now we want the original molarity, so we have to use the original liters. Don't get caught up into adding this back in. I want to use the original liters so I can get the original molarity. On 7, we have a buffer system because we have a weak acid in the conjugate base, and we have a admittedly fake pKa, but that's fine. And the pH of the solution is 4. So which is greater, the HA or the A minus concentration? Well, since we have the pKa and the pH just handed to us, it's actually faster to use the Henderson-Hasselbalch equation. And all we need is the ratio, remember. We just want to know which one is greater. And we can even just take a rough approximation of the ratio. We just need to know which one's larger. So I put this into the Henderson-Hasselbalch equation. Subtracting this over gives me minus 0.4. And I take 10 to the power of both sides, which unzips the log and leaves the fraction. And then I have 10 to the power of negative 0.4. And I know that 10 to the power of negative 0.4 is going to be a number less than 1. So this fraction is less than 1, which means the denominator has to be greater than the numerator. Or if you want to find something close to actual values, we can do it this way. If pKa is 4.4, then the Ka is 10 to the negative 4.4. Now, if this was 10 to the minus 4, we'd know that it was 1e negative 4. But this is more negative, it's smaller. So the actual value is going to be smaller. When we use a smaller exponent, we get a smaller value. So this is going to be smaller than 1e negative 4. It's going to fall into the e negative 5 range. And this looks like it's 40% of the way down to negative 5. But logarithms are more effective at the beginning than it seems. So I'm going to guess that instead of 40% of the way down and stopping at 6 down from 10, that it was 60% effective. And it went down 6 spots from 10 e negative 5. And it stopped at 4 e negative 5. At least I can't be too bad. So also I know that the pH 4 means that the H plus molarity will be 10 to the negative pH value, or 1e negative 4. Now, if that's the value for this, it's also the value for this. Disregarding what the H plus value was from pure water, if you make one of if you destroy one of these, you make one of these and one of those, and the previous amount of the H plus doesn't count enough to be worth anything, so let's just disregard it. These numbers are equal. So if this is 1e negative 4, that's 1e negative 4. Now I can do Ka equals products over reactants to the power of the number in front. But remember, this and that are the same thing, so I end up with that squared. So this is 1e negative 8 because you add the exponents on 10 when you multiply two numbers. And this swaps places and we get this. So 1 over 4 is 0.25. When you're dividing, you subtract the exponent on 10 on the bottom. So we get minus 8 minus a negative 5. So we get 0.25e negative 3. Well, just to make sure that we're really doing this straight up and we make sure of our answer, let's put this into standard scientific notation, because then we'll end up back in the e negative 4 and we can compare our numbers real easy. So if this number is going to get digit dot and put the decimal here, right here, this number got bigger, meaning this number must get smaller. So we get 2.5 e negative 4. And how does that compare? Well, remember, this was 1 e negative 4. So this number is bigger than that number by a factor of 2.5. HA is greater than A minus, and we got the same answer. This time we actually have a pretty good idea of the factor it's bigger by, but to be fair, they didn't ask that, so this is probably the easier method. Before 8, I want to make a point. As H plus gets smaller and smaller, pH grows bigger and bigger because it's the negative of the log of this number. So as pH gets bigger, the underlying value gets smaller, and an integer move bigger in pH is a fall in the underlying value by a factor of 10. So getting smaller is a rise in the underlying value by a factor of 10. And pKa and Ka work the same way. So when we say that pH is 4.3 and pKa is 3.3, this is bigger than that by a factor of 10 in underlying values. The Ka is bigger than the H plus by a factor of 10. The other thing to remember is that a buffer system achieves a pH because of the ratio of the molarities, not actually what the molarities are, but simply the ratio of them. So if we know the ratio, we know everything we need to know. You can make a buffer about a million different ways as long as the ratio between the molarity of the weak acid and the conjugate base is the same. So here's our weak acid deprotonating into the conjugate base. And probably the easiest way to do this is with the Henderson-Hasselbalch equation. So let's just put in the pH and the pKa. When we subtract, we get 1. When we take 10 to the power of both sides, we get 10 to the first power, which is 10, equals this. Therefore, the denominator must be greater, right? By how much? Well, when we move this up and over, we find out that HA times 10 equals A minus, or that this is 1/10 of that, isn't that? It's the same statement. Or this is 10 times greater than that, isn't it? Now, to do it sort of the hard way, we could say because they're negative logarithmic, 3.3 is 10 times bigger than 4.3. And all we're talking about is the ratio. So let's just pick an easy to work with ratio. So this is, so the Ka is 10 times bigger than this. And remember, these are going to be equal because when you make one of these, you get one of those. And we're going to, again, disregard all the H plus that was in the water from the dissociation of water naturally, because it's just too small to count. So let's ignore it. So one of these is made and one of those. So these two numbers are equal. So let's just set this as 0.1 and this as 10 times greater, which is what we said Ka is 10 times greater, as 1. Now this is times that, so that's squared. And when we move this up, we have that HA is 0.01. When we compare that though, this is 0.01 molarity. And remember the A minus was 0.1. So again, you have to multiply this by 10 to achieve A minus, or this is 10 times greater than that, which is the same answer either way you cut it. On 9, here's the titration curve if we use a strong base on a weak acid. So this pretty clearly is the equivalence point. This is the midway up the almost vertical line. This is the turnover point from going slightly one angle and then over to the other angle. If that occurs at 60 milliliters or darn close, then 30 milliliters or darn close must be the halfway point. So this is the half equivalence point. just FYI. So they used 5 milliliters of the weak acid, and then they titrated it to the equivalence point uh, and beyond, right? So if you used 6 times as much acid, where would the equivalence point be? Now, remember, the pH is based on the ratio in the buffer system. So the pH of the equivalence point and the pH of the halfway point or the half equivalence point wouldn't change. The vertical part wouldn't change, but it would take more base to get you there if you have more moles of acid, because using more acid, more milliliters, has more moles in it. So it would take 6 times as much base to get you there. So instead of the halfway point arriving at 30 milliliters, it would arrive at 180 milliliters. So the whole graph would stretch out by a factor of 6, although the vertical spots on the pH scale wouldn't change. This says the milliliters of base needed for every point, W to Z, would stretch out right by 6 times, but the vertical nature of those points wouldn't change. On 10, they talk about K1 and K2. And why do we need to know a K2? It's because we're going to talk about the second H coming off of sulfurous acid here. How do I know it's the second one? Well, it used to have two, now it has one, and then it has none. And we're talking about the transition between this and that. So that's the second H to come off. So we're talking about K2. So if the pH is 7, what's the H plus molarity? Well, it must be 1 times 10 to the negative 7, right? So if we set up our reaction and what essentially is our Ka expression, this is the Ka, it's K2. This is the H plus molarity, and these are unknown, but when I solve for the ratio of these and I divide under, I get 1, which means that these are equal when pH is 7. On 11, we have K, which is a classic supersoluble on an anion. And if we put it into water, we know all the Ks will come off, leaving only the anion. Now, if we give H plus into that same system, some of those H's surely will go and stick to the anion, because we also are told that the acid version of that anion with the H stuck on here is a possibility. It has a Ka, it is a real acid. I mean, it's not a strong acid, but it is a real thing. So the possibility of this anion that breaks off of the K absorbing, so to speak, sticking to H's coming off of this is a real thing. It will happen to some extent. And so what's the net ionic equation? Well, we have the anion plus the H plus, and of course they combine, and that's our net ionic. In B, we're going to put a strong acid in with essentially the anion, remember, because the Ks are going to come off. And we're going to hit the equivalence point, which means that all the anions have accepted an H onto them. And we remember, we know the ratio is 1 to 1. So if we can find the moles of H plus, that's also the moles of the anion. And we know the anion was in this many liters from before, so we can get the molarity. On C, let's solve the pH at the equivalence point first. And what do we need for that? The H plus molarity, or the OH minus molarity, but that doesn't really come into this because we're dealing with an acid. So what we'll be able to find is H plus molarity, which works just great for us. So this says a strong acid and the weak acid's conjugate base, the strong acid and the conjugate base of the weak acid, will go strongly to the right. So this will happen pretty well. Now, the original moles we have back here, remember? And if they all get converted into HA, then that's the same number of moles there. However, it's in a new amount of liters because we poured two solutions together. And just for ease of calculation, I went and called that 30 milliliters so that we have 45 from the previous page and 30, and that makes 75 milliliters. We get a new molarity of the HA acid. Now remember, this is what's happening, right? So some of this will dissociate into this and that, and these numbers will be equal because we're going to disregard the amount of H plus that comes from water naturally because it's too small to matter. So we get this. And of course, everything's to the first power because all the coefficients here are 1. Here's the K that they gave us. And we know this from here. Remember, that's the starting molarity. And we're going to do this also. We're going to do minus X and cross it out because it's not going to matter because that K value is more than 3 decimals smaller than this. So minus X won't affect anything. Let's just forget it. And of course, these are multiplied by each other at the top, and they're both unknown. So we're going to multiply and then square root, and we get X, and X, remember, was the value, among other things, of the H plus. It was the value of either one of these, but what I want to concentrate on this. And X is the value of these two, and I want to concentrate on the H plus. So that's the value of the H plus molarity, and negative log of that answer is the pH at the equivalence point. Then we have a question that really could come up on the real test, which is what kind of indicator would you want to use? And we have a list here. And here's the idea. We want something with two colors, otherwise we wouldn't notice the difference, right? So maybe it goes colorless to red like phenolphthalein does. Now, presumably, when this gets more red than clear, that's about the time I'll notice the color change. So that would be at roughly the halfway point, wouldn't it? Or pretty close. When this becomes the predominant color, that's about the time I'll notice it. So what I want to know is, where is the halfway point for this? And remember, the half equivalence point, or the halfway point, is where the pKa equals the pH. So the half equivalence point for thymol blue is when the pH is 2, because at that point, at its halfway point, its pKa equals its pH. So when will this change colors? Pretty darn close to when the pH is 2, because that's its pKa. Why did I pick that? Because I want the color change to happen at pH 2.54 or really close. So the color should change about pH 2, which is really close to this. And maybe I'll just make it a little bit more basic than that, so that the pH is really more like this than pH 2. But I have an indicator when I'm really close to this pH, which is the equivalence point, the end point of the titration. The half equivalence point of a thymol blue buffer will be at pH 2. So it should change color around that point. On D, I want the pH at the half equivalence point. Now that's where half of this has gotten turned into that. So these numbers are equal, which means the fraction is 1, log of 1 is 0, and this whole thing just crosses out. See, this is equal to 1, log of 1 is 0, and therefore pH equals pKa plus 0. So it just is the pKa, and pKa is negative log of the Ka, which they already gave me before. Remember this? So I can take negative log of that, and I have the pKa, which again, in this case, at the half equivalence point, is also the pH. On E, they want you to sketch a titration curve, and they're giving you the initial pH and the equivalence point. And they're going to want to see if you just draw a line or some other thing. Remember, it's going to fall off a bit. It's going to flatten out largely and then take a drop through there, almost vertical, and then flatten out a bit. I don't think they're going to argue about how far this goes out, because it depends on whether you actually did that part, right? Maybe you didn't, so there isn't any data out there. So they just want to see the general curve here, and that the halfway point, the half equivalence point, is in the middle of the flat-ish spot. And how do we know that that's the halfway point? Because the turnover from one slope to the other is about 30 milliliters used. And so the halfway point must be about 15 milliliters used. On F, the pH of the soft drink under discussion is 3.37 after the addition of the, remember this is the anion, right? So we added the base. Remember the K doesn't figure into pH or acidity. Now, which is in greater concentration, the acid version or the base version? And they really want to see some logic. You can't just say which one is greater. You must justify your answer. And they still do this occasionally, to say justify your answer. So I've got two ways for you. One is that at the half equivalence point, when these are equal, then pKa is the pH. Well, I know the pKa because I did that above. So at the half equivalence point, remember I found the pKa, that would be the pH. But this isn't the current pH. So we're not at the half equivalence point. The pH is lower than that. So the current situation is more acidic than the halfway point when these are equal. it's more acid than the halfway point when these are equal. So which one is present in greater amounts? The acid is. Now, just to be extra nerdy about it, I went and found some actual values. Take the Henderson-Hasselbalch equation, put in the pH current, the pKa value, subtract over, and you get negative 1.4 equals the log of the fraction. What I'm going to find is the ratio. If I can find the value of the fraction, I have the ratio between these two because that's what that is. It's a ratio. So to undo the log, I take 10 to the power of both sides. This unzips the log and gives me just the fraction. What's the left side though? It's 10 to the minus 1.4. And remember, I get a calculator and that's this. And that is roughly 1 over 25. So this is about 25 times greater than that.